Hey, Global Impact students, this is Mr. Ellinger, and this lesson is on quadratic equations. Our learning targets for the lesson: we want to be able to solve quadratic equations by factoring, and we want to be able to solve quadratic equations by graphing. Some essential understanding for you for the lesson: the zeros of a quadratic function y equals ax squared plus bx plus c can be found by solving the related quadratic equation 0 equals ax squared plus bx plus c. So the connection there is that we need to figure out where does the quadratic function have y values of 0. Some quadratic equations in standard form can be solved by factoring the quadratic expression and using the zero product property. The real solutions of a quadratic equation show the zeros of the related quadratic function and the x-intercepts of its graph. Some background for the lesson: the zeros of a quadratic function are equivalent to the x-intercepts of the graph of the function where y is 0. Thus, finding the zeros of the quadratic function is a way of solving the related quadratic equation set equal to 0. The following are equivalent: the zeros of a quadratic function, the x-intercepts of the graph of the function, the solutions of the related quadratic equation set equal to 0. To solve a quadratic equation by factoring, you rely on the zero product property. Assume that a and b represent any number or expression. The zero product property makes sense. For any product to be 0, one or both factors must be 0. Okay, so our first solving technique that we're going to look at here is by factoring. So let's discuss the factoring process here briefly. Factors of a given number are numbers that have a product equal to the given number. Factors of a given expression are expressions that have a product equal to the given expression. Factoring is rewriting an expression as a product of its factors. You can factor many quadratic trinomials in the form ax squared plus bx plus c into products of two binomials. You can use the distributive property or the FOIL method to multiply two binomials. You can use FOIL in reverse to help you factor. So for instance, the binomials x plus 4 times x plus 2 shows us how we would multiply those out. We would get x squared plus 6x plus 8. And then the backwards FOIL, if you will, or the reverse of FOIL, it's showing us the FOIL process there. To factor x squared plus 6x plus 8, think of FOIL in reverse. Find two binomials for which the first terms have products of x squared. The products of the outer and the inner terms have the sum 6x, and the last terms have the product of 8. So there you see that interpreted in terms of this factoring. So as these numbers here, 6 and 8, are more complex, have more factors themselves, especially the 8, and it may be helpful to make a table because some of the time it's just a matter of more of a guess and check method. Okay, so what is the expression in factored form? X squared plus 9x plus 20. Step 1, we need to find factors of 20 with a sum of 9. Since both 20 and 9 are positive, both factors are positive. So the factors of 20 are 1 and 20, 2 and 10, and 4 and 5. And then the pair of factors that has a sum of 9 is 4 and 5. Okay, so we know our two binomials are going to have a 4 and a 5 in it, both positive. So we use the factors we found. Write the expression as the product of two binomials, x plus 4, x plus 5. And, as a check, we can always FOIL this out, very, very quickly. X times x is x squared. The outer x times 5 is 5x. 4 times x is 4x. The outer and the inner product are always going to add together to be this middle term here, which is 9x. And then 4 times 5 is 20, so that's the correct factorization. So keys to being successful with factoring is recognition. You have to recognize the expression that you're being asked to factor. Is it a trinomial? Is it a perfect square trinomial? Is it a sum or sum and difference of cubes? Is it a difference of squares? Is it just a factoring where you can only factor a greatest common factor? And then remembering the techniques for each one of these. So let's take a look at a few more examples here. We need to find factors of negative 72 with a sum of 14 because our trinomial is x squared plus 14x minus 72. Since c is less than 0, one factor is positive and the other is negative, since c is negative. Since b is positive, the factor with the greatest absolute value is going to be positive. So factors of negative 72 are negative 1 and 72, 2 and 36, negative 3 and 24, negative 4 and 18, negative 6 and 12, negative 8 and 9. Now there are other factors of negative 72, but we're only listing the ones that fit these conditions here, okay? So knowing what our answer has to look like helps us kind of narrow in on these factors of, in this case, negative 72. So which ones have a sum of 14? Well, we just check them out here, and we find right here is our pair, negative 14 and 8. So we use those factors, negative 14 and 8, and we write our two binomials, x minus 4, x plus 18. Another example with a little twist in it, we have negative x squared plus 13x minus 12, and this negative in front of x squared can be problematic. But what we can do is we can rewrite the expression to show a trinomial with leading coefficient 1. So we factor out the negative, okay? Factoring out a negative out of a trinomial or any expression basically changes the sign of everything that's left. Okay, so we're just doing a sign change here. We want a sign change on x squared. So we factor out the negative 1 and we're left with x squared minus 13x plus 12. Find factors of 12 with the sum of negative 13. Since c is greater than 0, both factors have the same sign. Since b is less than 0, both factors must be negative. So again, here are our clues how this is going to play out. So factors of 12 both have the same sign, and in this case are both negative. Negative 1 and negative 12, negative 2 and negative 6, negative 3 and negative 4, which one have a sum of negative 13? Well, that's negative 1 and negative 12. So what we do is, this negative sign that we factored out here, that's going to be in our answer. Okay, that can't go away. We have to remember to put that in our answer. And then the factoring that we did on what was left after we factored out the negative gave us x minus 1, x minus 12. So if we don't factor out that negative, our answer could look slightly different. We could still factor it, but it would just be a little more complex in terms of how we would come about getting our answer. So factoring out a negative is a trick to always keep in mind. It comes in handy from time to time. All right, another type of factoring that we have to be able to do, and sometimes, you know, the factoring that we were just looking at, factoring a trinomial into two binomials, doesn't work because we either don't have a trinomial, or maybe we have to factor out a greatest common factor first before we factor the trinomial. So the greatest common factor of an expression is a common factor of the terms in the expression. It is the common factor with the greatest coefficient and the greatest exponent. You can factor any expression that has a GCF not equal to 1. So part A here we have 6n squared plus 9n. Okay, so we have to determine here, well, first of all, it's not a trinomial. So we know it's not going to factor into two binomials. So we just look at our two terms, 6n squared and 9n, and ask ourselves, what is the biggest number that divides into both 6 and 9? Well, that's 3. And look at our two terms. Both of them have n in them. What's the lowest power or least power of n that's in both? And that's n. And so our GCF in this problem is 3n. So what we've got to do is we have to factor out the GCF 3n. Now remember, what it means to factor out a GCF, it means to divide all the terms by the GCF. And so when we do that, what we need to do is we need to figure out what is left in our expression after we factor out the GCF. So here in this first expression, they have shown what happens when you break up a term into a product of its GCF and whatever is left in that term. And I think this intermediate division step here kind of clues us in on that. So we have 3n times the quantity 2n plus 3n times the quantity 3. So here you have the 3n that's common in both, and so we pull that out or factor that out. And so we get 3n times the quantity 2n plus 3. So the technique that I was demonstrating here is once you determine the GCF, if you divide both of the terms by the GCF, then we can write our answer as the GCF times whatever's left after we factor out the GCF. So a couple different ways to write it here. This step here may not be necessary as long as we understand there's some division that's going on and then how to write our answer once we've done that division. Okay, so B here we have a trinomial this time, so we could look at this and say, okay, chances are this factors into two binomials. But the problem is we have this leading coefficient on x squared of 4. And whenever we get these leading coefficients on x squared in the a spot, it makes things more difficult to factor into two binomials. So what we can do is we can just examine this and say, well, can I factor out the 4? Or whatever that leading coefficient is. And in this case, the answer is yes. 4 divides evenly into 4, 20, and 56. So what we'll do is, when we'll look at the rest of this here, is there an x in all the terms? And that answer is no. So the GCF here in this problem is 4. And anytime we can factor out a GCF, it always makes life easier later on. So if we factor out 4 of everything, okay, divide everything by 4 or rewrite everything as a product of 4 and something, then we can go to this step right here. And so we have our 4 in front of our parentheses, and then what's left inside the parentheses is x squared plus 5x minus 14. And that's a much simpler trinomial in terms of its factoring. We just have to figure out what two numbers multiply to be -4 and have a sum of 5. Okay, that's much simpler to do than this original expression here. So we know that -2 times 7 multiplies to be -14, and those two numbers add together to be +5. So this trinomial that's in the parentheses here factors into x minus 2 and x plus 7. But we can't neglect or forget to remember the 4 that we factored out in the beginning of the problem. Okay, that's still a part of our solution. That's still a part of the expression. We've just factored it out, but we still have to include it in our answer. So there's a way that the GCF combined with factoring a trinomial into two binomials makes things easier for us. Here's a trinomial 2x squared plus 11x plus 12. And you might look at this and say, oh, I can just factor out the 2. Maybe this is like the example that we just did. Well, I can't factor out a 2 here because 2 does not divide into 11. So when we have a trinomial and it has a leading coefficient other than 1 on x squared, we have this method called the AC method. So step 1 says, since there is no common factor, we need to find the product of A and C. So A is 2, C is 12. The product of A and C is 24. Since both B and AC are positive, find factors of 24 that have a sum of 11. See, what we're doing here is we're still doing the factoring that we did on the easier trinomials where there is no coefficient here. We're just using this extra step here, this AC product, to help us find factors, okay? So factors of 24 are 1, 24, 2, and 12, 3, and 8, 4, and 6. The one that has a sum of 11 is 3 and 8. Okay, so once we determine this pair, it's going to play out a little bit differently, okay? We're going to take our original trinomial 2x squared plus 11x plus 12. What we're going to do is we're going to take the 11x and we're going to rewrite it as a sum of two terms. So 2x squared plus 3x plus 8x. And the 3 and the 8 come from the pair of factors that we determined with our technique here. All right, and what we're going to do is we're going to arrange these in a way so that when we factor something out of these two and factor something out of these two, in this case an x here, and in this case a 4 here, can be factored out of these groups. This is called factoring by grouping. What's left after we factor out the x in the first grouping and the 4 in the second grouping, we're left with binomials that are the same. So in this first product here, we have a common factor of 2x plus 3 that's also in this second product here, which means we can factor out 2x plus 3 out of both of these products, and that leaves x plus 4. So that gives us our answer here, okay? And again, this is called factoring by grouping. So we rewrote bx as a sum, 3x plus 8x. We found a common factor for the first two terms and another common factor by the last two terms, and rewrite using the distributive property. All right? Now you might ask, well, what if I does it matter if I put these in this order or another order? Okay, what if I wrote when I was splitting up my bx, what if I wrote 2x squared plus 8x plus 3x plus 12? You see I switched the 8x and the 3x. Would it still work? We'll take a look here. What could I factor out of these first two terms? I could factor out 2x. And what would that leave? X plus 4. In the second grouping here, what could I factor out? I could factor out a 3. What would be left? X plus 4. Common factor of x plus 4 in both. So I factor out an x plus 4 from both of these. So out of this one and out of this one. So factor out an x plus 4, and what's left? 2x plus 3. So I get the same result. Okay? So the key is splitting up this bx term and then arranging them in a way that the factoring, we can proceed with our factoring, okay? And this is called factoring by grouping again, okay? All right, another special type of trinomial that we have is called a perfect square trinomial. And I will let you read there about a perfect square trinomial, but basically a perfect square trinomial is going to be one of the form. A big clue is if our coefficient on A and our C are both perfect square numbers, big clue that this is going to be a perfect square trinomial, okay? And so what can happen is we use our sign, say, okay, plus sign here, that means both the signs of my binomials are going to be the same. Minus sign here on the B term tells me that they're both going to be subtraction signs. So what I can do is this kind of gives me a shortcut if I recognize the perfect square trinomial part. What's the square root of 4? That's 2, so this is going to be a 2x. We got a subtraction sign in here because the signs tell me. Square root of 36 is 6. So this perfect square trinomial is going to factor into 2x minus 6, quantity squared. Okay, now along those lines, some more squares. The difference of two squares, the expression a squared minus b squared is the difference of two squares. And there's a pattern there. So if you have something squared minus something else squared, it's a big clue that this is a difference of squares, and it actually does factor into two binomials, even though it doesn't have a third term, a trinomial. So here's an example of how this plays out. I recognize, okay, I've got 25x squared minus 49. So there's a difference. 25 and 49 are both perfect square numbers. Big chance that this is a difference of squares. So I think about what is 25x squared. Well, that's 5x, that quantity squared, minus 7 squared. And then once I have those two terms broken down into squares, then it's just a matter of taking each of those terms and writing them as a sum and writing them as a difference. Okay. Now, why this works? You know, if I just use this as an example, if I were to FOIL this back out, I would get 25x squared. My outer product would be minus 35x. My inner product would be positive 35x. And my last would be minus 49. So when I go to combine terms here in the middle, I get 0. So what's left is 25x squared minus 49. So that's why that x term is missing, if you will, in a difference of squares. All right, so let's talk about how we use this to solve quadratics after we've done a quick review of factoring. Wherever the graph of a function f of x intersects the x-axis, f of x equals 0, okay? On the x-axis, all the y values are 0 regardless of where we are, so they have function values of 0. A value of x for which f of x equals 0 is called a zero of a function. And it doesn't matter what type of function you're working with, wherever the function crosses the x-axis, we call that a zero. To find zeros of a quadratic function y equals ax squared plus bx plus c, we're going to solve the related quadratic function 0 equals ax squared plus bx plus c. So we're determining where does y equal 0. You can solve some quadratic equations in standard form by factoring the quadratic expression and using the zero product property. Basically, the zero product property says, hey, if two things multiply to be 0, then one or both has to be 0. And that kind of makes sense. The only way that you can get a product of 0 is if one or both things are in fact 0. So what are the solutions of the quadratic equation x squared minus 5x plus 6? Well, we factor the thing first. So x squared minus 5x plus 6 factors into quantities x minus 2 times x minus 3. And the zero product property says we're going to take each one of these expressions, and we're going to set them both equal to 0. So x minus 2 equals 0 and x minus 3 equals 0. Solve both of those for x. X equals 2, x equals 3. So one of those has to be true, or both has to be true, but in order for either one to be true, we have to figure out where x is 0. So the solutions that we get from those are x equals 2 and x equals 3. Okay, so that's solving by factoring using what's called the zero product property. What are the solutions of the quadratic equation 2x squared plus 7x equals 15? So here's our problem. Okay, and sometimes we'll have this constant term or another term on the other side of the equal sign. What has to happen first is we have to subtract all the terms, or get all the terms on one side so that we have 0 on one side. This is the only way that we have standard form. Okay, all the terms have to be on one side with a 0 on the other side. Okay, so once we write this in standard form, then we've got to factor our trinomial here. So you'll notice here we've got a 2 coefficient on x squared. So the first question is can we factor out the 2? Well, quickly we'll see here these are both odd numbers, so we cannot factor out the 2. So using our AC method, we need to look at 2 times negative 15, which is negative 30. So we need to find factors that have a product of negative 30 and have a sum of 7. Okay, so some numbers that multiply to be negative 30. We got 1 times 30 is a possibility. I'm just focusing on the 30. 1 times 30, 2 times 15, 3 times 10, 6 times 5. Okay, now knowing that the product has to be negative 30, one of these has to be negative and one of them has to be positive. So the bigger number is going to be positive in these pairs. So 3 and 10 have a difference of 7. So if the 10 is positive and the 3 is negative, that's what we're looking for here. So we're going to rewrite our trinomial. Okay, so I arranged our terms this way just because I know that 2 and 10 have a common factor there of 2, so that makes it a little easier for me to see how I want to arrange those terms. So, again, we're factoring by grouping, so we're gonna use these first 2 terms, and then we're going to use these second 2 terms to do some factoring. Okay, just out of those 2 terms. So 2x squared and 10x, we can factor out a 2x, and that leaves x plus 5. And then in our second grouping here, we can factor out a negative 3, and that leaves x plus 5. Okay, and when we have these signs in here, we've got to be a little bit careful, but we have to remember we want our signs to match up. We want this binomial to match up with this one, so we may have to tweak the signs a little bit. But in this case, since these both have subtractions, I'm going to try factoring out a negative 3. And that's probably going to always be the case because I don't really want a negative sign on x here. Usually we don't want that. So this is how I factored it. And then you see I've got an x plus 5 in both of those terms. So we'll just go ahead and factor out an x plus 5 from both. And then whatever is left goes in our second binomial. And so there is our factoring. Okay, now we're not done. We have to actually solve the quadratic. So here's where the zero product property comes in. So use blue here. We take our first expression, set it equal to 0. And then we'll take our second expression and set it equal to 0. So solve this one for x. We get x equals negative 5. Subtract 5 from both sides. Here we will add 3 to both sides first. And we'll have 2x equals 3. Divide both sides by 2, so x equals 3 halves. So our solutions are x equals negative 5 and 3 halves. And what's going to happen is after you do a couple of these, you're going to notice that when we have just x here, the solution is always the opposite sign of the term here. So when it says x plus 5, the solution is going to be negative 5. So a lot of times some of these you can do in your head. These, when you have a coefficient on x, it's a little more difficult. So if you're going to try and do it in your head, you need to be very careful about how you go about doing it. Make sure you're processing it the right way. A lot of times I'll see 2/3 here wind up being the answer just because we get in a hurry. just slow down and write it down. Maybe at least do the first step of adding 3 to both sides, and then it'll help you keep straight what's going on. All right, so you know, I know a lot of times we think we can do everything in our head, but I just encourage you to take the extra 5 seconds to write your work down. Okay, so here's an application. So from the time Mark Twain wrote The Celebrated Jumping Frog of Calaveras County in 1865, frog jumping competitions have been growing in popularity. The graph shows a function modeling the height of one frog's jump, where x is the distance in feet from the jump's start. So here we have a quadratic curve, a parabola, that models a jump of a frog, okay? So from that model, we will be able to determine the height of the frog's jump, its max height, and then we will also be able to determine its distance, okay? So how far did the frog jump? The height of the jump is 0, okay, at the start and into the jump. So this frog starts off here where I'm coloring this blue dot. It jumps in the air, it's in the air, it's in the air, and boom, right here, it's back on the ground. So our graph here, the frog, the two variables in this are the distance and the height. So this is the distance and this is the height. The horizontal axis is distance and the vertical axis is height. So at distance 0, the height is 0, and at distance, whatever this distance is out here, the frog's height is also 0. And then somewhere along this graph, there is a distance where the frog reached its maximum height. So we can determine those different points and those different values by analyzing our graph and our function here. So here's our function. We cannot solve that function by factoring, so we will use our technology here. And these screens that they're showing you are from a TI-84, but we can do this on a TI Inspire just as easily. If we go to our graph, open up a graph sheet, go to our function editor entry and type our function in, press graph. We should be able to see this. Depending on the window that opens up, you may have to resize it a little bit, but a couple things to remember. We're doing a problem that involves distance and height, so we only really want to be focusing on the first quadrant. This parabola, this mathematical model, has parts that are not in the first quadrant, okay, because a parabola has an infinite domain. X can be anything, and it's going to have parts of its range that we're not considering. Like, for instance, in this picture over here, this part of the graph, we're not going to consider that because those are heights that are negative, and we don't, we know that we can't have negative heights. So we will come over here and analyze our graph. At x equals 0, at a distance of 0, the height is 0. The frog is just taking off, and so as the frog jumps, this parabola models the jump here. Okay, so somewhere around here, it's going to reach a max height, and then over here is where it lands again after jumping. And so what we can do is we can use some different functions on our calculator to find those points. Okay, and once we have our graph, we can analyze the graph and we can find the zeros. Okay, so if you press the menu button and do a graph analyze, you can actually calculate the zeros. All right, and you can also calculate the maximum. Those are both options under that menu. Okay, we can use those functions on our calculator to define these values. We find that at 20.34 feet is when the frog is landed. Okay, and that's where we can find the zero of a function. And then we can also find that the frog jumped to a height of about 3 feet by calculating the maximum of that quadratic function. And both of those values we can get from our calculator using our technology. That's about the only way that we could do this. All right. We could get the zeros a different way, which we'll look at later. The maximum we would need to use our technology. Okay. So a third question here: what is a reasonable domain and range for such a frog jumping competition? So while the function y equals negative 0.029x squared plus 0.59x has a domain of all real numbers, actual frog jumping does not allow negative values. So a reasonable domain for frog jumping distances is, say, 0 to 30. Reasonable range is 0 to 5. Okay, this frog, its heights and distances both fell within that range. Maybe we can assume that there's not going to be any frogs that are going to jump farther than 30 feet. This one was 20 feet, so another frog would have to go 10 more feet, which is pretty crazy. and a reasonable range 0 to 5. You know, maybe a frog could jump a little higher than 5 feet. I don't know, but that would be a reasonable domain and range for such a function and such a problem. Okay, so another example of this, that last example is an example of what's called projectile motion. Here's another example of projectile motion. A kicker punts a football. So this is what the trajectory would look like. The problem that I have here is kicking a soccer ball, but you get the idea here. So it says the function y equals negative 0.03x squared plus 1.6x models the path of a kicked soccer ball. The height is y, the distance is x, and the units are meters. How far does the soccer ball travel? How high does the soccer ball go? Describe a reasonable domain and range for all functions. So I'm going to let you use your calculator, and I'm going to let you calculate those things and come up with those solutions. And then I will just demonstrate this on the calculator to make sure that we're all on the same page and make sure that you got the right answers. Okay? So go ahead and try that on your calculator now. Pause the video, and when I come back, we will do that. All right, so what we're going to be doing here is we're going to be analyzing our quadratic function here to model our soccer ball. And what I've done is I've gone ahead and entered the function in to the calculator. I've gone ahead and graphed it, and I changed the viewing window a little bit. That way I can see the whole graph, at least the parts that I'm concerned with. You know, since we're doing a problem here involving a real-world situation, we're really only going to concern ourselves with the first quadrant. So I want to make sure that I can see all of the graph in the first quadrant. Now, the things that I want to be able to look at, I want to see the max height of the soccer ball, and I also want to see the total distance that the soccer ball traveled. So let's talk about the total distance that the soccer ball traveled. At the origin here, we have 0, 0. We have the starting point of the soccer ball, the flight of the ball. So at distance 0, distance traveled, the height of the ball is 0. And then as that ball is kicked, the path of the ball is modeled by this parabola. So what we've got to do is we've got to figure out what is the x-intercept over here. What is the 0 of the quadratic function at this value here, okay? And the calculator will do that for us. So what we've got to do is we've got to go to our menu. We're going to analyze the graph, and we're going to have it calculate the zeros for us, right? So the lower bound, remember the lower bound meaning like how far left, okay, what's the least x value that you want the calculator to look for the 0. So somewhere to the left of the intersection, click, and then go somewhere to the right of the intersection, and you'll see that the 0 is highlighted in this gray strip, and there the calculator approximate our 0 for us, 53.3333. So 53.3 is the distance that the ball traveled, okay? And now we also want to use the calculator to help us determine the maximum height of this ball. So, you know, again, it's going to be the maximum, the vertex of this parabola. And we could do this algebraically, but since we're on here, we can go to let the calculator do it for us. So analyze the graph, and this one is a maximum. So again, lower bound, how far left do you want it to look? Well, it's somewhere to the left of the vertex here, and then go over somewhere to the right of the vertex there, and it tells us our maximum value is 26.66, repeating. So 26.7, approximately 26.7 is the maximum height of that soccer ball, all right? So again, pretty powerful stuff here. The problem is, you know, and I mentioned this in classes, you know, coming up with this model would be difficult. If we weren't given the model, then we would have a difficult time doing this. But since we have the model, we can go ahead and do some analysis with that model to answer these particular questions using our model. So that's how we can use our calculator to do some of this stuff for us. Okay, so we talked about how to solve these quadratic equations, and getting other pieces of information using our technology. So, as we go along here, our calculators are going to come more and more handy, because as you can see here, these numbers, when we're talking about real world situations, are not always nice whole numbers that are easy to work with, right? So we have to be able to use our technology, and we have to be able to use it efficiently. So that's it for now. Hope you guys have a great day.